Most people think of a language model as something that writes. A word appears, then another word, then another. And for GPT-style models, that is basically right. The model predicts the next token, appends it to the context, then predicts the next token after that. This left-to-right loop is so familiar that it can start to feel like a law of nature. But it is not. It is a design choice. A very successful design choice, but still a choice. Autoregressive language models turned next token prediction into the foundation of modern AI. That one loop shaped almost everything around them. Key value cache, prefill and decode, streaming interfaces, batching strategies, speculative decoding, serving latency, and the economics of inference. The reason your chatbot can start responding before it has finished the answer is because the model is naturally producing text one token at a time. But that same structure also creates a bottleneck. If token number 50 depends on token number 49, and token 49 depends on token 48, then generation has a serial dependency built into it. You can parallelize the neural network operations inside each step, but the sequence itself still advances one committed token at a time. So the question is not, are autoregressive models bad? Clearly, they are not. The question is, what if language generation did not have to look like typing? Diffusion language models start from a different picture. Instead of generating a sentence from left to right, imagine beginning with a damaged sentence. Some tokens are missing. Some positions are uncertain. Or in continuous versions, the whole sequence begins as a noisy, latent representation. Then the model refines it. One pass fills in some structure. Another pass cleans up contradictions. Another pass sharpens word choice. The output emerges through repeated denoising. This is why the analogy to image diffusion is useful, but only up to a point. In image diffusion, a model can start from noise and gradually resolve a picture. Early steps capture rough structure. Later steps refine details. For text, the same basic idea is tempting. Do not commit to the first word, then the second word, then the third. Instead, allow the whole sequence to be uncertain and let the model revise many positions while seeing context from both directions. That gives diffusion language models a very different set of strengths. They are naturally suited to infilling. They can condition on text before and after a missing span. They can revise earlier positions instead of treating every generated token as permanent context. And because multiple positions can be updated in the same denoising step, there is at least a possible parallelism story. But possible is the key word. A diffusion model may update many tokens at once, but it usually needs multiple refinement steps. If it takes too many steps, the parallel advantage can disappear. You are no longer paying for one token at a time, but you may be paying for many model calls over the same sequence. So, the trade-off changes. Autoregressive generation is serial over positions. Diffusion generation is iterative over refinement steps. That is the core shift. There is a reason diffusion took over images, video, and audio before it took over language. Those media types are naturally continuous. Pixels, waveforms, spectrograms, and visual latents can be noisy in a smooth way. A slightly wrong pixel can still be close to the right pixel. Text is different. A token is discrete. The word cat is not a slightly noisier version of the word car. One token flip can change syntax, meaning, factuality, or code correctness. This creates a representation problem. If you want to build a continuous diffusion model for language, you need some latent space where text can be denoised. But that latent space has to do two things at once. It has to be smooth enough for diffusion, and it has to preserve enough information to decode back into exact tokens. That second part is brutal. If the latent compresses too much, the diffusion model becomes easier to train, but the text representation loses detail. You can generate something fluent looking, but not necessarily something that preserves token-level fidelity. This is where AURORA-LM becomes interesting. The paper's core move is not just use diffusion for text, it is to push back against the usual compromise. Instead of simplifying the representation to make the generative model's job easier, AURORA-LM keeps a high-capacity, decodable text latent, then designs the diffusion model to learn that harder distribution. That is a more ambitious bet. It says, do not shrink the language representation until diffusion can handle it. Make the diffusion model handle a representation that can still decode accurately. AURORA-LM separates the problem into two pieces. First, it builds a decodable text representation. It uses a query-based encoder-decoder to organize text into what the authors describe as a high-capacity, prefix-aligned latent sequence. Think of this as building a latent draft of the text that still contains enough structure to be decoded back into tokens. Second, it trains a diffusion model over that latent representation. The model is called a block-causal diffusion transformer. The block-causal part matters because Aurora is not simply denoising one entire unlimited sequence all at once. It still has a causal structure across blocks. But inside a block, positions can be denoised in parallel. So it is a hybrid shape, left to right at the block level, parallel refinement inside the block. That gives the system a bridge between language's sequential structure and diffusion's refinement structure. The paper also adds several engineering details around noise calibration and self-trajectory consistency. The simple version is this: training sees sampled noisy states, but inference is an iterative process where the model's own previous denoising steps affect the next step. Aurora tries to reduce that mismatch. The reported results are promising, but they should be framed carefully. Aurora reports strong performance among evaluated continuous and diffusion-based language models on open web text free generation and XSum summarization. It also reports that a 1 billion parameter version can match or surpass a size-comparable autoregressive model under the author's matched evaluation protocol. That is not the same as saying diffusion language models have beaten frontier GPT-style systems. It means one of the core obstacles, continuous, decodable text representation, is getting more credible. The second reason this topic matters now is scaling. A new architecture is interesting in a paper. It becomes important when people start asking how it scales with model size, data, compute, and inference constraints. That is what LLaDA MoE version 2 is about. The paper studies mixture of experts' diffusion language models. In an MoE model, the full model can contain many expert networks, but each token only activates a subset of them. This lets model capacity grow without increasing active computation proportionally. That trick is already central to many large autoregressive models. The question is whether the same scaling intuitions carry over to diffusion language models. LLaDA MoE version 2 suggests, not exactly. The authors report that optimal batch size grows faster with compute than in autoregressive models. Optimal learning rate decays faster. ISO-flop analysis tilts slightly toward more data. Larger scales favor larger expert pools at fixed activated capacity, and moderate expert granularity remains consistently effective. The headline system they train is a 30 billion parameter model with 3 billion active parameters, trained from scratch on 23.5 trillion tokens. The paper says that with about 65% as many pre-training tokens as Qwen version 3, it approaches Qwen version 3 on several knowledge, reasoning, and coding benchmarks. Again, the point is not to turn this into leaderboard hype. The real point is that diffusion language models may have their own scaling rules. If that is true, then you cannot simply copy the autoregressive recipe and expect it to work. Batch size, learning rate, expert layout, data allocation, and inference strategy may all need to be retuned for the denoising regime. That is what makes this a systems story, not just a modeling paper. If diffusion language models work well, where would they matter first? Probably not ordinary streaming chat. Autoregressive models are almost perfectly matched to the chat interface. They can begin speaking immediately. The user watches the answer stream out. The infrastructure is mature. Diffusion is more interesting in tasks where the final text is not naturally a one-way stream. Editing is the obvious example. If you ask a model to rewrite a paragraph while preserving some constraints, a bidirectional refinement process makes intuitive sense. The model can see the whole draft, revise multiple positions, and make global adjustments instead of committing to a prefix. Infilling is another example. Code completion often needs the model to understand what comes before and after a missing block. Autoregressive models can be adapted for this, but diffusion-style masking makes it a native operation. Structured generation is another possibility. If the output has global constraints, a table, a JSON object, a plan, a patch, a refinement process could potentially repair inconsistencies across the whole object. And then there is hybrid inference. Nematron Labs diffusion points toward a future where one model might support multiple modes: autoregressive decoding, diffusion decoding, and self-speculation. In that world, the question is not which paradigm wins forever. The question is which generation mode fits the task. Streaming answer? Autoregressive may still win. Batch rewrite? Diffusion may help. Code infill? Maybe masked denoising? Fast draft plus verification? Maybe self-speculation. That is the more realistic future. Not one decoding loop for everything, but a runtime that chooses the right generation regime. There are also good reasons to be skeptical. First, denoising steps are not free. Updating many tokens in parallel sounds faster, but if the model needs many refinement passes, the speed advantage can vanish. This is why so many diffusion-LM papers focus on blockwise decoding, adaptive decoding, few-step generation, distillation, or hybrid modes. The inference story is still unresolved. Second, production infrastructure is built around autoregressive decoding, key-value cache, streaming, continuous batching, speculative decoding, quantization recipes, serving frameworks, monitoring, tooling. Autoregressive models have a massive deployment advantage because the ecosystem has spent years optimizing that loop. Third, evaluation can lie. One recent failure mode paper makes this especially clear. Low perplexity in continuous diffusion language models can be driven by repetition. A model can look good under a metric while producing text that repeats too much. That is not a small footnote. It means diffusion language models may have failure modes that familiar metrics understate. And fourth, language has a strong left-to-right prior. Humans read sequences. Code executes in order. Many tasks naturally unfold step by step. The autoregressive factorization may be limiting in some ways, but it is also well aligned with how many text tasks are consumed. So the honest conclusion is not, next token prediction is dead. It is, next token prediction finally has credible alternatives worth taking seriously. The important shift is conceptual. For years, large language models have mostly meant one thing: predict the next token, again and again, at massive scale. Diffusion language models ask whether text can be generated more like a draft being refined than a sentence being typed. AURORA-LM attacks the representation problem. How do you build a continuous latent space for language without losing the exactness of tokens? LLaDA MoE version 2 attacks the scaling problem. If diffusion language models are going to grow, what rules do they follow? Neither paper proves that GPT-style decoders are going away, but they do show that language modeling is no longer a single paradigm story. The future AI stack may include models that stream left to right, models that refine whole spans, models that infill bidirectionally, and models that switch modes depending on the job. Next token prediction built the current era. The next era may be about choosing when not to use it.